faithfully sharing insights, exploring great books worldwide.
Hi there, this is Sally's Book Talk. Today, I'll be breaking down the book The Black Hole War for you. Its author is the renowned American physicist Leonard Susskind. Susskind is a world-class authority in theoretical physics, a member of the U.S. National Academy of Sciences, and one of the founders of string theory. In 1981, Susskind first met the British physicist Stephen Hawking at a physics gathering. That year, Hawking was 39 years old, intellectually extraordinary, and full of confidence. When someone asked Hawking a question, his initial reaction was always absolute silence, but his final answer was often incredible. The smile on his face said, "You might not understand what I'm saying, but I know I'm right." It was at that gathering that Hawking made a bold assertion. Information is lost in black holes. This assertion was bold because it violated the law of conservation of information, meaning information changes form but is never destroyed. The law of conservation of information is one of the most important laws in physics. Physicists like Einstein, Oppenheimer, and Feynman built and refined quantum mechanics based on this law. Quantum mechanics and general relativity are the two pillars of modern physics. Choose. If Hawking was proven right, and black holes could destroy information, quantum mechanics would be fundamentally in crisis. To defend the existing edifice of physics, scientists launched a 26-year-long black hole war. The author of this book, Susskind, was also involved. As a defender of quantum mechanics, he and other scientists jointly confronted Hawking's challenge. In this book, Susskind details the entire course of this war. What secrets do mysterious black holes hide? Can black holes really destroy information? Next, I'll interpret this grand scientific discussion and explore the secrets of black holes from three aspects: the origins, debates, and outcomes of the black hole war. The black hole war revolved around a key question. Does information falling into a black hole really get lost? So, this involves two issues. First, why do quantum physicists believe information cannot be lost? Second, how did Hawking make information get lost in black holes? First, let's talk about why information cannot be lost. In physics, information isn't something ethereal. It must be recorded and attached to matter. Particles like molecules, atoms, and photons can all store varying amounts of information. In this sense, information is tangible and intrinsically linked to matter. The total amount of matter in the universe is finite. Correspondingly, the total information storage capacity of the universe is also finite. Moreover, this total information is conserved. This leads us to a crucial law in physics, the law of information conservation. It states that information can't be created from nothing nor vanish into nothingness. But the state of information can change. For example, the same carbon atoms arranged one way become graphite. Arranged differently, they become diamond. Different arrangements represent changes in information state. Thus, we get different substances, but no matter how information transforms, it can never be lost or destroyed. It never vanishes from the universe. Take burning a book. You're left with ashes. If you could collect every atom from the ashes and precisely measure all properties in the smoke and thermal radiation, you could theoretically reconstruct the burned book. The book's information remains in the universe, not lost, just harder to retrieve. Informational explanation is quantum mechanics' cornerstone since it deals with probabilities. We describe particles' probability distributions, not definite states.
Regardless of individual probabilities, their sum must always equal 1. 100%.
If probabilities didn't sum to 1, the world would descend into chaos, making calculations impossible. Information conservation dictates this fundamental operating logic of physics. Information can be combined, split, or transformed, never created or destroyed. But collectively, it can always be fully restored to its original state. Yet Hawking argued black holes could violate information conservation, causing permanent loss. This brings us to the second question. How did Hawking make information disappear in black holes? It starts with understanding black holes' nature. A black hole is a celestial body with such intense gravity that it acts like an eternal prison. Once matter or light enters, it's trapped forever with no escape. Therefore, we can never see what's inside a black hole.
The structure of a black hole presented to us is extremely simple. To describe one, you only need three parameters.
Mass, electric charge, and angular momentum. Angular momentum is a parameter related to rotation. Once you know these three quantities, you know everything about it. In the universe, you probably can't find anything simpler than a black hole. Because diverse celestial bodies and matter all contain vast amounts of information. For instance, Earth contains information about plant and animal life. Mars contains information about craters, volcanoes, and canyons. Even a tiny sugar cube contains information about the motion of billions of molecules. But black holes? Among thousands in the universe? To distinguish them, you only need to observe these three quantities: mass, charge, and angular momentum. Mass. Beyond that, there's no difference between black holes. American physicist John Wheeler, who coined the term black hole, invented a saying called the no-hair theorem. It means a black hole is like a bald head. Besides mass, charge, and angular momentum, these three hairs, it has no other information hair. But Hawking added a bit more hair to the hairless black hole. He proved that black holes also have temperature, a view that was shocking at the time. People generally believed black holes had no temperature. They were at absolute zero. Why shouldn't black holes have temperature? Because any object with a temperature above absolute zero can produce thermal radiation, which emits particles. But black holes have gravity so strong, they don't even let light escape. They only take in, so how could they radiate particles? But Hawking used rigorous calculations to prove that black holes do radiate particles. This is the famous Hawking radiation, one of Hawking's most important theoretical contributions. And so, how do black holes emit radiation? To understand this radiation, we need some knowledge of quantum mechanics. In quantum mechanics, when there's an energy fluctuation in space, a pair of particle and antiparticle can spontaneously appear. One carries positive energy, the other negative energy. They collide and annihilate in an extremely short time, so it doesn't violate energy conservation. We can't observe these particles, so we call them virtual particles and virtual antiparticles. Virtual meaning illusory. Hawking discovered that when these two particles appear near a black hole, something strange happens. One particle falls in while the other escapes. Most commonly, the virtual antiparticle falls into the black hole while the virtual particle escapes. The virtual antiparticle carries negative energy. When absorbed by the black hole, it cancels out some of the black hole's energy. So, according to the mass-energy equivalence, losing energy means losing mass, so the black hole becomes lighter. Meanwhile, the escaped virtual particle carries positive energy. Without its antiparticle partner to annihilate it, it becomes real and remains in the universe. But thus, the net effect is equivalent to the black hole emitting particles while losing mass. This outgoing particle stream is Hawking radiation. Here's the problem. For ages, people thought black holes were eternal like diamonds. Once formed, physics suggested no mechanism could destroy or eliminate them. But Hawking radiation showed black holes constantly radiate and will eventually evaporate completely, like summer pond water drying up. This seemingly eternal prison will vanish, taking all trapped information with it, violating information conservation completely. Thus, a powder keg in theoretical physics was ignited. The black hole war erupted in full force. Susskind said when he heard this information paradox, he was thrown into utter confusion. Meanwhile, Hawking seemed to dance excitedly on quantum mechanics' grave. Not just Susskind, the entire physics community debated this paradox fiercely. Next, we'll cover part 2, the great debate of the black hole war. Addressing this physics problem, the most straightforward solution is observation.
But here's the frustration. We can never observe Hawking radiation. Why?
Because according to Hawking's temperature formula, larger black holes are colder, while smaller ones are hotter. Radiation flows from hot to cold, so only relatively hot black holes might show observable radiation. This means black holes need extremely small masses, but real ones have stellar scale masses, making them freezing cold, constantly absorbing energy rather than evaporating. To put it simply, a black hole capable of hawking radiation is like a pot of boiling water, radiating heat into the air. But real black holes are like ice cubes just taken from the fridge, not radiating heat, but absorbing heat from the air. For the ice to release heat, the surrounding air would have to be colder than the ice. It's estimated that the universe will need billions of years before temperatures might drop below those of black holes. Only then will black holes begin to evaporate. Worse still, black hole evaporation is extremely slow. It takes at least 10 to the 60 year to observe any change in mass or size. Therefore, it's utterly hopeless for humans to resolve the black hole information paradox through observation. So solving this problem relies solely on theoretical thinking. Scientists have roughly formed 4 viewpoints. The first viewpoint directly sides with Hawking, believing that information is indeed lost. The scientists in this camp are primarily general relativists. General relativity and quantum mechanics are 2 relatively precise theories in physics. One governs large-scale celestial bodies, the other governs small-scale particles. Although each theory is perfectly self-consistent, their foundational theories differ, making them incompatible, which is not all for everybody. And Hawking himself was a general relativist. He proposed that black holes can destroy information, threatening the fundamental laws of quantum mechanics, but posing no direct threat to general relativity. Thus, almost all general relativists accepted Hawking's conclusion, thinking that if there's an error, it's quantum mechanics that's at fault. This is clearly unacceptable to quantum physicists. Many opposed undermining fundamental laws and thus proposed the second and third viewpoints. The second viewpoint holds that information isn't lost, just hidden, stored in the remnants of black hole evaporation. According to this idea, when a black hole's mass decreases to that of a speck of dust, it might stop evaporating, leaving tiny remnants like an information basement, where all the information swallowed by the black hole is tightly sealed in this minuscule space. This is a well-known viewpoint for resolving the black hole information paradox. But Susskind disagreed because it implies that an infinitesimally small particle could hide any amount of information, finite space storing infinite information, which isn't allowed, making this viewpoint untenable. The third viewpoint is quite sci-fi in nature. But this view suggests that deep inside a black hole, a fragment of space detaches to form a tiny self-contained universe called a baby universe. All information swallowed by the black hole enters this baby universe. Unlike the second viewpoint, where black hole remnants containing information remain observable in our universe, but the baby universe exists in space-time completely separate from ours. So we can neither observe nor communicate with it. It's like a damaged hard drive. Information isn't deleted but remains inaccessible. Though this solves information loss, Susskind saw unobservability as equivalent to loss, unacceptable to him. None of these 3 viewpoints satisfactorily resolve the black hole information paradox. As a quantum physicist, Susskind saw cracking this puzzle as a war to defend quantum mechanics.
He obsessed intensely, dreaming of Hawking choking him, waking drenched in sweat.
Amid contemplation, he discovered a 4th approach entirely different from the others. This approach centers on the black hole's boundary, the event horizon. The event horizon is the boundary separating the black hole from outer space. And as objects approach, gravity intensifies. At the point where light can't escape, they reach the event horizon. Crossing it means no return. The event horizon is a one-way door, entry only. Thus, a black hole's size refers to its event horizon area. But regardless of size, black holes have finite mass and volume. This implies an upper limit to their information capacity. What happens if we keep throwing things into a black hole? Well, when full, information should leak out. But the event horizon, a point of no return, prevents escape. Susskind believed the solution lies at the event horizon. So what secret does it hide? Next, let's explore part 3, how Susskind used the event horizon to resolve the black hole information paradox. To solve the paradox, we must understand where information falling into black holes goes. As mentioned earlier, information requires storage. It's an entity almost like matter. Naturally, we'd assume storing it occupies space. But here comes a counterintuitive revelation. The maximum information a space region can store isn't determined by its volume, but by its surface area. Confusing? What's this got to do with black holes? Let me explain in detail. Scientists discovered that when black holes absorb matter, they grow, not just in mass, but also in surface area, meaning their event horizon expands. Imagine a black hole as a balloon. The event horizon is its rubber surface. Absorbing matter and information is like inflating the balloon, expanding its surface area. Fascinatingly, this expansion follows precise rules. Calculations show that, regardless of initial size, every bit of information added increases a black hole's event horizon by exactly 1 Planck area. Bits are information's smallest units. Planck areas are space's smallest units, creating an extraordinary correspondence. 1 bit per Planck area means a black hole's total information equals its event horizon's total area. Simply put, information equals area.
This seems unbelievable. Even physicists were baffled. Why area instead of volume?
After all, information is material. This suggests wasted internal space. But physics defies intuition. This information-area relationship appears not just in black holes, but all around us. Susskind illustrates with Egypt's Library of Alexandria, history's oldest and grandest library.
Suppose we divided space into Planck units, physics' smallest volume units.
Then, let's cram every unit with information. So, theoretically, this library can hold up to 10 to the 149th power bits. But in the real world, nature can't pack every volume unit full. Information distribution has to follow certain rules.
Therefore, practically, this library can only store up to 10 to the 74th power bits, way less than 10 to the 109th.
Now, the Egyptian king finds out that the enemy has hidden secret information in the library.
He passes a law banning the hiding of any information.
To follow this law, all info has to be written on the library's exterior walls. Even though it's a waste of space, it's the law. But how much info can actually fit on those outer walls?
The calculation comes out astonishing.
The bit count that fits on the outer walls is precisely 10 to the 74th power. This is one of modern physics' most mind-blowing discoveries. The max info you can store in a space equals its surface area, not its volume.
Are you still confused after hearing this?
This sounds totally counterintuitive, way beyond everyday experience and imagination, super abstract. You probably can't picture how this works, but it's all from physics formulas and math calculations. Let me give another example, photos. We all know photos. Photos are obviously 2D images, but we can see 3D info in them. People and scenes in photos have layers and depth. They look 3D. This shows 2D surfaces can store 3D info, and 3D movies make it super obvious. Images on a flat screen turn into vivid 3D scenes with 3D glasses, optical trickery, but photos and movies can't store full 3D info. They only show one angle. We can't see the sides or back. So, is there a way to store a whole 3D scene on 2D film?
Sure thing, that's holograms.
Holograms are made by recording objects on holographic film with a special camera. Holographic film ain't like regular film. It shows a messy pixel grid, not an image. Faithfully sharing insights, exploring great books worldwide. Hi there, this is Sally's Book Talk. Today I'll be breaking down the book The Black Hole War for you. Its author is the renowned American physicist Leonard Susskind. Susskind is a world-class authority in theoretical physics, a member of the U.S. National Academy of Sciences, and one of the founders of string theory. In 1981, Susskind first met the British physicist Stephen Hawking at a physics gathering. That year, Hawking was 39 years old, intellectually extraordinary and full of confidence. When someone asked Hawking a question, his initial reaction was always absolute silence, but his final answer was often incredible. The smile on his face said, "You might not understand what I'm saying, but I know I'm right."
It was at that gathering that Hawking made a bold assertion. Information is lost in black holes.
This assertion was bold because it violated the law of conservation of information, meaning information changes form but is never destroyed. The law of conservation of information is one of the most important laws in physics. Physicists like Einstein, Oppenheimer, and Feynman built and refined quantum mechanics based on this law. Quantum mechanics and general relativity are the two pillars of modern physics. If Hawking was proven right, and black holes could destroy information, quantum mechanics would be fundamentally in crisis, in nothing. To defend the existing edifice of physics, scientists launched a 26-year-long black hole war. The author of this book, Susskind, was also involved. As a defender of quantum mechanics, he and other scientists jointly confronted Hawking's challenge. In this book, Susskind details the entire course of this war. What secrets do mysterious black holes hide? Can black holes really destroy information? Next, I'll interpret this grand scientific discussion and explore the secrets of black holes from three aspects: the origins, debates, and outcomes of the black hole war. The black hole war revolved around a key question. Does information falling into a black hole really get lost? So this involves two issues. First, why do quantum physicists believe information cannot be lost? Second, how did Hawking make information get lost in black holes? Actually, the entire field of the black hole war has moved beyond empirical verification. Researchers essentially operated in lofty mathematical realms. In this domain, theories are validated by logic rather than experimentation. You might ask, isn't science an empirically based knowledge system? How can we rely solely on logical verification? Exactly. While logical consistency can't prove truth, it can disprove falsehood. If a theory contains mathematical contradictions, it's wrong without needing experimental proof. When scientists mathematically verified the holographic principle and related complex string theories, the results were consistent. The equations held up. These theories may or may not reflect nature, but they mathematically refuted Hawking's arguments. The black hole war finally ended in 1998. Hawking's deteriorating condition nearly cut off his communication with the world. Unaware of physics developments, he needed time to process the changes. In 2007, Hawking formally admitted information could escape black holes without vanishing. The black hole war officially concluded. That's the story of the black hole war. Though Hawking conceded defeat, his physics legacy remains untarnished. At Hawking's 60th birthday in 2002, Susskind addressed the gathering. He said, "Scientifically, my relationship with Hawking was adversarial. But among all physicists, Hawking influenced me most profoundly. Nearly every problem I ponder concerns the fate of information in black holes." His profound proposition forced us to rethink physics foundations, leading to new models. This is Hawking's monumental contribution. The black hole war dramatically advanced physics.
Many believe physics' ultimate theory of everything, unifying relativity and quantum mechanics, lies in future black hole research.
All right, that concludes the black hole war. Find reading notes below the audio. Until next time.